of next
Sorry,
over
I
the
forgot
course
the
of next
recording.
thanks. So yeah, over the course of the next 40 minutes or so, I want to make the case for how factor graphs are a powerful and flexible tool for solving many modern day robot perception problems. And in this talk, we'll focus on three principal challenges to make these tools work across a broader class of problems in robotics. Okay, so let's begin with a brief glimpse into how SLAM has evolved over the years. SLAM has had a rich history going back to the 90s, where early methods formalized the SLAM problem to localize a robot in unknown environments using relatively simple yet noisy sensors. As time progressed, we moved on to richer sensors like cameras, LiDARs, depth sensors, and were able to localize across longer distances in more complex environments. Now, state-of-the-art algorithms are powerful enough to run online on board a computer, handling multiple loop closures. And these methods are heavily being used today by self-driving, UAVs, virtual reality, amongst many other such applications. However, this is but the tip of the iceberg. So as we develop new sensors and applications, we are seeing an increasing variation in the demands from robot perception. And here are just a few such examples, such as estimating objects from touch sensors, mapping using both audio, visual information, processing language and visual information for scene understanding. So the question is like, can inference tools from SLAM be also used to solve such problems? And what are some of the challenges that would need to be addressed? So let's take a step back and think generally about the perception problem. I like to think of this ancient parable that summarizes essentially the essence of perception. It's a story of an elephant and a group of blindfolded people trying to make sense of what they are perceiving. So you can think of the elephant here as the latent state X that needs to be estimated. However, each person only gets a local glimpse into the state in the form of local touch measurements that you see as Z1, Z2, Z3 here. And each measurement independently only tells a part of the story. But if we combine all these measurements together, we can actually solve for the true state X. So more formally, we can solve for the inference problem, probability of states X given measurements Z. So now let's come back to robotics, where we consider this problem of a robot hand manipulating a cube. Now, oftentimes the robot cannot see the cube, maybe because it's occluded by its fingers, or it's retrieving the cube from a bag or reaching from top of a shelf. Touch, in such cases, can provide local yet precise information about the state of the cube. So what makes this problem hard? Suppose each finger here has a tactile sensor, which provides a rich image of the local deformation at the fingertips, as you can see in the bottom left corner. The images here are capturing the local contact patch about the point of contact as the object moves with respect to the fingertip. Now, a single such image only gives us partial information about the state, which here is the object pose. And it alone isn't enough to localize the object. We hence need to be able to reason over multiple such images so as to collapse uncertainty on our state. So formally, this is the inference problem that we'd like to solve. Given a stream of noisy high-dimensional measurements, infer a sequence of latent states in real time. And we are going to model this inference problem as a factor graph. A factor graph is a graph with two types of nodes. The first type is a latent variable to be estimated. For example, the object pose x naught at time t equal to 0 is a variable node. The second type of node is a factor node, which encodes relationships between these variables. For example, here, the factor phi models the dynamics between poses x naught and x1. Now, as the robot finger pushes the objects, we keep adding new variables and factors into the graph. Note that if we are just using the dynamics or the motion model, our estimates will drift over time. Now, this is where the tactile images come in. Images at any two time step can tell us how much the object has moved by. And we can incorporate this information in the graph via an observation model as a factor between two poses. So in this instance, that information is being incorporated between poses x1 and x3 via an observation model, or also known as like a loop closure factor here. So now we hence end up with this factor graph representation of the problem, where the x's here are the unknown latent states, and the phi's are the factors or the potential functions. Now, the objective then is to determine the most likely states, x hat, that maximize the product of all these factor potentials. Now, while this optimization may seem expensive as the number of variables keep growing in time, there are efficient solvers out there that leverage the sparsity of the graph to solve this problem in an online incremental fashion, thus ensuring real-time performance. So we now have this factor graph framework that lets us incorporate structural priors, do real-time inference, and also capture higher order dependencies in the graph in the form of loop closure factors that we looked at briefly earlier. And with this framework now, let's go into the three principal challenges that we propose to address in this thesis. So in challenge one, we look at the problem of efficient representations. A common goal in SLAM is to create a map by fusing several measurements together. So for example, here you see an occupancy map on the right that is being created by fusing measurements from the different states, x0 to xt, from the graph on the left. Now, note that these maps in turn are used by downstream modules, such as a planning module. And this actually poses two competing demands on the map. The SLAM module demands efficient updates so that whenever the graph optimizer computes new solutions, it doesn't have to recompute this map from scratch, while the planning module demands efficient queries so as to be able to get free space information efficiently. And existing methods fall on a spectrum where purely local approaches based on submaps are deformable and hence efficient to update, whereas while the purely global maps fusing measurements together are efficient to query. But the trade-off here is in the corresponding query and update times. So the question that we want to look into is, can we get the best of both worlds on this spectrum? Now, let's move to challenge two, where we look at the problem of constraints from physics. Now, consider the example here, where we are estimating the pose of an object being pushed around by this KUKA arm. Now, we as humans know that the arm cannot physically teleport through the objects. And this information becomes especially critical, like when estimates are being used downstream by a planning module that expects these estimates to satisfy some physics constraints. However, existing incremental solvers can only solve for unconstrained objectives. So the question that we want to look into here is, can we extend these incremental methods to also incorporate for hard equality and inequality constraints? Now, finally, in challenge 3, we consider the problem of rich observations. Now, consider here this example where we must estimate the object pose from a high dimensional tactile image data. Now, again, like if you look at any one image here, it's really hard to say anything about the underlying object pose. Many different object configurations can result in the same contact patch image that we see here. On the other hand, though, if you look at multiple such images, it is possible to infer how the object pose is changing over time. But to do that, we need observation models that can map these multiple images into states X in the graph. And these models are hard to engineer for such tactile sensors that are capturing local contact deformation information in the form of RGB images. So the question here is, can we learn such observation models that can be directly optimized by the factor graph? Okay, so this puts all the challenges together in one picture, where in the first challenge we have maps efficient to query and updates. In the second challenge, we looked at incorporating physics-based constraints in the graph, and in the third challenge, we looked at incorporating high-dimensional observation models in the graph. And if you're able to address propose methods in these challenges, this thesis will make these methods applicable to a wider variety of problems in robotics. And we'll measure progress by evaluation over various data sets and some choice applications. So these data sets are a collection of real and synthetic problems from two main categories, robot manipulation and navigation. And our target application is object pose estimation from tactile measurements for two different tasks, planar pushing and in-hand manipulations. So while the focus of this talk is mainly on challenge 2 and 3, we will briefly touch upon one. So in challenge 1, as you recall, we wanted to have a map representation that was both efficient to update and query. And existing methods fell on a spectrum where purely local submap-based maps are deformable and efficient to update, but expensive to query by the planner, while fused global maps are efficient to query, but expensive to update from the SLAM optimizer. And we present a hybrid map representation that can provide us with the best of both worlds, with efficient queries and bounded updates. And our insight essentially was to do incremental updates on the map rather than having to fuse and recompute the map from scratch. And we do this by exploiting sparsity in the underlying SLAM graph and the fact that one can efficiently add and subtract measurements from an occupancy map. And just a quick look at the result. So we evaluated our method on both synthetic and real data collected from an underwater robot that maps with sonar sensors. And the plots on the right show that our hybrid method, as shown in red, has the best trade-off between queries and update times. Okay, so now that we've briefly looked at challenge 1, let's now move on to challenge 2. So in challenge 2, if you recall, we wanted a way to enforce hard constraints in factor graphs. For example, we don't want the robot arm here to teleport through this object. So how do we do this? So we consider both equality and inequality constraints. For example, a gripper pushing an object on the left induces equality constraints, uh, while a robot navigating within a corridor should satisfy inequality constraints induced by the corridor boundaries as seen on the right. So how do we formalize this intuition? And let's start by writing out the old inference objective that we saw, which was to estimate the most likely states given all measurements until the current time step. To solve for this inference objective efficiently, a common assumption is to model the factors phi as Gaussian, followed by linearization. And this results in an unconstrained linear least squares objective that can be solved for iteratively. So that is the objective that you see in the bottom right corner. We now add constraints to this problem. So similar to the objective that we saw earlier, the constraints too are linearized. The equality factors are shown in red and are represented by the G matrices. And the inequality factors that are shown in orange on the left are represented by the H matrices on the right. So as a result, in every iteration, we solve for a quadratic program instead of the unconstrained quadratic that we saw earlier. And to put this in context, here's a brief map of related work on factor graph optimizations. And we can think of two axes, methods that tackle unconstrained versus constrained problems, and methods that operate in batch versus incremental modes. And while there has been a fair amount of work on these quadrants, we look at the fourth quadrant of extending these incremental approaches to solve for a constrained optimization objective. Okay, so let's begin by first looking at how the unconstrained least squares problem is solved for efficiently. Now here, delta x is the update to the states x every iteration, and A is the matrix that is derived from linearizing all factors. Now, since the graph is sparsely connected, the resulting matrix A is also sparse. As a result of which, this sparsity can be exploited by computing a square root factorization of A into an upper triangular matrix R. And once we have the matrix R, we can efficiently solve for delta X via back substitution. Now in this problem, while we are exploiting sparsity, we are still having to recompute this factorization R from scratch every time step as new measurements come in. So the key insight behind the incremental solver ISAM that we will use is that as new measurements come in, we can directly update the R matrix RT from the R matrix from the previous time step, that is RT minus 1. And this avoids having to factorize the full A matrix from scratch. So now in the unconstrained solver that we just saw, the two main advantages are that it's exploiting sparsity and the incrementalness or the online nature of the data. The shortcoming, however, is that it cannot directly handle constraints. So we present a framework, ICS, or incremental constraint smoothing, that solves for a constraint problem efficiently by leveraging primal dual methods. In particular, we use the augmented Lagrangian method that solves this problem as a two-player game. So the two players here that we mention are the primal and the dual solvers. And both these solvers together are optimizing for a single objective that you see below. And this is the original unconstrained objective that we saw earlier, with the A delta x minus b, augmented with penalty terms for the constraint violation. Now, the primal solver minimizes this objective over delta x, which you recall were the state updates, while the dual solver maximizes over the dual variables VU, which control the weight on the penalty terms. So at any given round, the primal solves an augmented quadratic objective to compute delta x, keeping the duals V and U constant. And the dual solver solves for the duals VU, or also the Lagrange multipliers, keeping delta x constant. And this happens iteratively until a convergence criteria. And the key advantage to doing this is that even though we have a constrained objective, the primal solver here is still solving an unconstrained quadratic, which we know how to solve efficiently via sparse incremental solvers like ISAM that we looked at in the beginning. And the dual optimization here is simply a first order gradient ascent, which is incremental by nature. And this makes the overall ICS framework efficient. So let's dive into some results. This is the data set of a robot pushing a disk. The goal here is to track the disk with only binary contact measurements. And we enforce equality constraints that say at contact, the two shapes must touch each other. And we see that the incremental constraint solver is able to solve the constraints much more precisely than the unconstrained solver here, ISAM. And here's a more realistic example using the Pi bullet simulator, which shows that the constraint solutions are able to do the state updates along the surface of the object so as to prevent intersections between the end effector and the object shape. Whereas the unconstrained solver, which doesn't have the information of constraint, does the state corrections in any direction and not necessarily along the surface of the object. Okay, so, and we also evaluate this method on a different application of robot navigation where we enforced inequality constraints corresponding to the corridor boundaries that you see here in green. And the green essentially shows the active inequality constraint as the robot navigates through the map. And we can see here in the plot on the right and in the qualitative map on the left that the constraint solver is able to keep the mean constraint violations close to 0. And finally, one thing I want to touch upon is that one common trick with unconstrained methods is to tune the penalty weights so as to get them to satisfy constraints. So this is a plot showing the constraint violation against the tuning of the cost term weight. And we see that unconstrained methods can be very sensitive to the choice of weight selection and theoretically cannot drive the violation error completely to 0. The constraint smoothing framework is able to automatically vary the Lagrange multiplier terms VU so as to drive the gradients at the constraint optima to 0. So finally, we move to challenge 3. Okay, so let's return to the question that we posed earlier. If we are given just a single tactile image, can we say a whole lot about where the object is? So if you look at the image here, on the left, the tactile images are being generated from the pushing trial on the right. And just looking at the movement in the image, it's really hard to tell what the object pose would be relative to your sensor. So prior work has used learning only method or engineered functions within optimization methods. And both of these will have limitations because in the tactile image case, the partial observability makes it really challenging to learn a direct mapping between the tactile image and the object state directly. And one would typically need to use additional information such as a prior map as used in prior work. On the other hand, on the right, in optimization methods, engineering functions for high dimensional measurements for such sensors can be brittle and difficult to scale across objects and sensors. So our goal here is to learn such tactile observation models, which in turn can seamlessly integrate as factors within a factor graph during inference. And this integration lets us leverage benefits of both learning-based and optimization-based methods. So let's look at what the observation model mapping here is between the state and the measurement. So essentially by observation model, we mean the likelihood of measurements Z given the states X, which we, in the factor graph framework, we express as a quadratic objective under Gaussian assumptions. Okay. So on the left, as you see the contact patch moving, in the measurements on the corresponding state it changes, which is the sensor pose with respect to the object. So now the relationship that you saw, instead of learning a direct mapping between the images to the pose, which is hard, our key insight is to actually predict relative sensor poses about the contact point from a pair of tactile images. And this is what you see on the left, where there is a tactile image pair, which is getting featureized into this probability map and then key point features. And the displacement between these two features will map into a relative sensor pose about the contact point. And this is the relationship that we are interested in learning. So we do this with ground truth supervision during training during training time, and then use these resulting predictions as relative factors between non-sequential poses during the factor graph inference. And the idea here really is that as a result of predicting these relative sensor pose transformations, we can correct for the accumulated drift in the object pose estimates. And observation models trained in this fashion can work across a large class of objects as long as the local contact surface patches are in the distribution of those found in training data. And in addition to the tactile predictions that we looked at earlier, we also incorporate engineered physics and geometric models into the graph. So the physics models here are based on the quasi-static pushing dynamics, and the geometric models are based on intersections between object and end effector and penalizing such intersections. So we evaluate our approach for now tracking object poses during planar pushing tasks. And this is the work from home lab at Stuart's home. And you see here the experimental setup on the left, which has the motion capture system. And on the right are close-ups of the object, end effector, and the digit tactile sensor, which is what we use for experiments. The motion capture system on the left is recording ground truth, object, and end effector poses for us to train and evaluate our tactile observation models. So here is an example of a typical planar pushing trial with a rectangular object. So the top left here shows the tactile images captured by the digit tactile sensor. And as the object is being pushed, we can see the contact image, the contact patch in the tactile image move around. And the patch moves depending on the relative orientation of the object with respect to the sensor pose. And we collect several such trials pushing 3 different objects over varying trajectories. Now here we see the outputs of the various layers of the keypoint feature extractor that we use. The features or the key points are able to track the contact patches in the tactile images on the rightmost column. And notably, different objects create different local contact patches. Okay. So now that we have this, let's look at the final task performance on object tracking. And I kind of want to highlight these 2 results, where on the left, we are using the learned tactile factors. And on the right, we are using what we are using essentially a contact detector, which is the information that one would get from a typical binary contact sensor. And for this trajectory, you can see that the contact detector only estimates on the right drift enough that it localizes about a completely a wrong contact point once we make and break contact. And here we show more qualitative results from 5 different trials pushing a rectangular object. And we compare against various baselines, notably the no tactile, which uses only the physics and geometric models, and the const tactile that you saw earlier, which was equivalent to using a contact detector without image information. And these are trials all collected from real data. The Oracle tactile here uses ground truth values. And we see that the learned tactile factors are able to reliably track the object over time, recovering poses close to their true trajectories. And here are similar results generalized to different object shapes, essentially a circular and an ellipse object. And we see similar trends where the learned factors are able to recover poses close to their true trajectory, matching the Oracle performance closely. And here are some quantitative results for a greater number of trials, of about like 150 trials for 3 different objects over sequences of 15 seconds each. And we see that with the learned factors, we are able to outperform baselines across the different objects. Okay, so this completes our challenges picture, where we looked at the 3 challenges and looked at certain methods to address these 3 challenges. So while our methods address these challenges partially, there are still several open problems left to address. And we now propose work to tackle some of these challenges. Okay, so let's dive into the proposed work. And going first into the proposed work 1, based on the challenge 3 that we just looked at. So if you recall, in challenge 3, we were learning observation models for tactile image data. And interestingly, during the course of our experiments, we noticed an artifact that, for example, in this planar pushing task, not all factor errors are equal. So if we look at the ground truth and compare it with outputs from various models, like the tactile model or the motion model, the tracking accuracy varies with the type of pushing motion. So for instance, like during the straight line sections where there aren't much relative rotations, the motion factors are more reliable than the tactile factors because of the quasi-static dynamics approximation being more accurate. On the other hand, during the curved portions where there are greater rotations of the object about the contact point, the tactile factors are actually more informative because there is a greater difference in the contact patch in the images. So there is a greater displacement in the corresponding features. And due to greater motion in these contact patches in the tactile images, we can recover more informative factors. So to incorporate this notion, our insight here is that we should not be training our tactile models in isolation. Instead, we should try to minimize the final graph optimization errors when training such models. So let's start with a factor graph optimizer here that you see on the top that takes as input a model C theta x with parameters theta and gives as outputs the optimized trajectory x star. And think of the model C theta here as a cost function that penalizes bad states. And that's what we show on the left as factor costs. And this is essentially the same map objective that the graph optimizer solves for, where the parameters theta here are the factor covariances and the factor network weights. And our goal is to learn parameter theta that finally results in an optimized trajectory x star that matches the ground truth trajectory xgt. And to do this, we'll use a loss function that measures mismatch between the ground truth and the optimized trajectory. And this is challenging to do directly because the naive graph optimizer that we use is not differentiable by nature. Hence, we cannot simply backpropagate through the optimizer so as to update theta. So, but fortunately, this problem here that we are looking at, which is learning observation models for estimation, is actually equivalent to a well-established problem in imitation learning literature, which is how can we learn cost functions in planning? So more formally, we can think of observation models in SLAM as cost functions in planning, ground truth trajectories in SLAM as expert demonstrations or trajectories in planning, and factor graph optimizers like ISM2 as non-differentiable black box planners in planning like A star. And as a result, we can borrow ideas from this method, learning to search from Rue-Bagnal's group, which learns cost functions from expert demonstration. And their key idea is to essentially iterate between guessing a cost function, planning with it to produce a path, comparing it with an expert path, and updating the cost to make this expert path look cheaper. And the estimation or the smoothing equivalent to this problem would be to iterate between guessing a factor cost function, running the black box graph optimizer, comparing with the ground truth trajectory, and then updating our factor parameters to make the ground truth trajectory look cheaper. And the nice thing about this method is that it does not require differentiability in the graph optimizer. Okay, so that was proposed work 1. And now let's look into the proposed work 2, which would be addressing challenge 2, which we looked at earlier on physics-based constraints in the graph optimization. So in challenge 2, when we talked about the incremental constraint smoothing solver, we made one critical assumption, which was that the linearization point is fixed according to whatever the R matrix that was computed at that time. If we remove that assumption, we would have to re-linearize every single time step, which can be very expensive. So why is this assumption limiting? Now consider this nonlinear function here. The linearization point xlin gives us the quadratic in purple, quadratic approximation in purple that we see here. Now, as soon as we move a tiny step to the right, as we update our most recent estimate, can see that the quadratic assumption in purple immediately becomes a poor approximation for the new estimate point, which is xs. So the orange should be the latest approximation rather than the purple. So how do we get ICS, or the constraint smoothing solver, to work with a moving linearization point? And we take the insight from ISAM2, which was to represent the R matrix that we saw earlier, the sparse R matrix with a base tree. And the advantage with a tree structure over a sparse matrix structure is that the tree structure decouples all the variables sufficiently so that whenever we need to relinearize, only a subset of the tree is edited, depending on which variables estimates have diverged from the past linearization point, and the rest of the tree remains untouched. So our approach of doing ICS with relinearizations would be in the primal solver where we used ISAM to replace that with using a base tree in place of R matrix. And we actually additionally needed to compute R transpose matrix with the constraint solver, which we will compute from the base tree by traversing it once. The dual solver actually remains unchanged since it was just a gradient ascent on the dual variables. And as a result of which we can get the best of both these approaches, which was handling relinearizations while being able to handle constraints. And finally, coming to proposed work 3, where our focus is more on the experimental evaluation of the methods that we talked about. So we talked about our target applications being tactile sensing for object tracking during manipulations using tactile sensors. And we propose to do this object tracking along 2 axes of motions, non-prehensile motions such as pushing, and in-hand motions such as in-hand object rotations. So let's look at task 1, since we briefly looked at that in challenge 3. And we propose to use the same setup here of planar pushing with a motion capture system, and use an end digit sensor mounted on an end effector that would push around different objects. So for instance, here it's pushing a rectangular object. For task 2, we propose to use an experimental setup with a teleoperated Allegro hand, where there is a digit sensor on each of the fingers, and there is a small object being rotated in hand, and the goal is to be able to track the pose of this object over time. Okay, so in summary, we looked at the 3 challenges, where first we looked at maps that are efficient to update and query between SLAM and planning. And challenge 2 looked at incorporating physics-based constraints in the graph optimizer. And challenge 3, we looked at how to handle high-dimensional tactile measurements within the graph optimizer. And as a timeline, we have a timeline of about a year from now. So in the months from December to March, we'd be looking at proposed work 1, which was the learning to smooth algorithm, followed by figuring out the logistics and setup for in-hand hardware and collecting data sets. And parallelly, we would be developing the constraint solver with relinearizations. And finally, we'd like to demonstrate our models for a task like in-hand tracking and tracking object states in real time there. And the last month would be on writing the thesis. So I'd like to thank my committee members now for all their feedback and helpful discussions, and also thank the 2 primary funding sources behind this work, ONR and Facebook AI Research. And I'd also like to thank all my many wonderful collaborators on the work that I presented today. my lab members at RPL, and the FRC RI community in general. Um, Thank you so much for your time, and I'd like to take any questions.